Hi everybody, this is Nafish. Today we are going to learn how to do a fast Fourier transform on sinusoidal wave, and we're going to use Python's Jupyter Notebook to do that. So as usual, we need to import the necessary libraries, NumPy, SciPy, and Matplotlib. Okay, and the sinusoidal wave is a times sine and then 2 times pi times f times t. This is usually the form we see in books and lecture notes. So A is the amplitude, F is the frequency, and T is the time duration. So let's formulate the signal first. So let's say our A amplitude is, let's say 1, and then we have our frequency, which is let's write it here, is F is equals to 1 over the time period. Now the time period, let's say it's 0.2, okay, just some number. And then also we need to have to define this t, the time duration, like how long the signal is going to run. So let's say t is equals to np dot a range. I'm going to explain it right now. 0 to, let's say, 30, and then delta t, and delta t is, when you have to define delta t, which is the sampling frequency. So let's say delta t is 0.1, just putting some numbers there, and let's say time period is 0.5. Okay, so t is equals to np dot a range. So what it's going to do, so we're going to get numbers from 0 to 30, and delta t, which is the spacing or the points or sampling, this is the sampling rate, you can say. Okay, so let's plot it out, plot the signal. So signal is equals to a. We have the value of a is 1, but you can put some other numbers if you want. Then the sine. Now we need to call the numpy np.sine, and then 2 times pi times f times t. Okay, so we have our signal. Let's run it, and let's see. Oh, okay, so pi, we need to write np.pi because this pi is in the np library. Okay, and it is saying a is not defined. Okay, because we did not run all these cells, so we have to run all the cells, and I think we are good. Let's plot this signal out. Okay, so plt, matplotlib, we need to call as plt. So plt dot plot, and then plot the signal. Let's visualize the signal. Okay, so this is our frequency. This is our sinusoidal wave. So one thing I would like to mention, remember we had the amplitude 1, so it goes from 1 to -1. We can have amplitude of 10, and this number is going to change. So you see the amplitude went from 1 to 10, and you can see like the frequency seems to be very high, so we can just have, like, let's say 2, and then run all cell, and see we have lower. So now the period is kind of higher. Okay, and so the frequency went to lower. It is inversely proportional. Okay, but we are going into all these electrical engineering things, so let's focus on this plotting. So we need to have x-axis t, and then the signal will be at y. So let's run it, and you can see our time duration, which goes from 0 to 30. You can call it 30 seconds. So it goes from 0 to 30, and then you have the amplitude, which goes from 10 to -10. Okay, now what we can do is we need to add some noise to the signal, and I'm planning to extract that signal from the noise, so by doing the FFT. So let's get into that. So what we need to do is just let's copy this part. Okay, and paste, and let's open up some more cells. And now our signal is this guy, but what we are planning to do is we are going to add some noise onto that. So signal plus let's say np dot random dot randn, and then len is going to be t. So we're going to add some noise on our original signal, some random noise, and the distribution is going to be from 0 to 30. That's why len is 3. Okay, and let's assign this to a new variable. So signal plus noise. Okay, just assign it over there, run it, and then let's see the signal with noise. Okay, so plt dot plot, and then time is the x-axis, and we have sig capital N. Let's plot it out. Okay, so you can see there is some distortion in the noise, but since the amplitude is like 10, we don't see much more, it's kind of clearly see some clipping on the edges, but it's not that much distorted. Let's have like equal amplitude of the original signal. So noise is also like, it's kind of magnifying the noise, okay? And let's visualize. I think it's going to be much more noisy. You see, the noise is kind of going all over the place, and now you can see even it goes over -40. Okay, but let's see whether our FFT is able to pick out the frequency from the signal. So remember, the frequency is 1 over time duration, and the time is 2. And let's do the FFT. To do the FFT, we need to call the FFT back. So signal with FFT, okay, is going to be SP. So the FFT back is in the SP Scipy library. So SP dot FFT, you press FFT and then tab, and it's going to show up the FFT back, and then do the FFT. Okay, and you're going to do the run the FFT on the signal with noise. Okay, so let's run that, and then we have the FFT signal. Now we need to get the power density. Okay, we're going to show what is the power density, or how much power the frequency component is carrying out. Okay, so to do that, power density is equals to our signal underscore FFT, and this is going to be complex number, because you remember, like if you do FFT, is going to, you're going to get a complex number. You can let me show that to you as well. Let's paste it here, and then you see we have all the complex number down there. Okay, so that's why we need to get the absolute value of the signal with FFT. Okay, and this ABS is in the numpy library, so np.abs in this guy, and then we need to do the square. Okay, so square, so power of 2. Okay, and now let's paste it here and run it. It says it's not defined because we did not run this line, and now it should be defined. Okay, so we got our power density, and we need to plot it against. So here the axis is time t, and the y-axis is amplitude. But when you are in the frequency domain, we need to plot it the power density, and then that's going to be across the frequencies. Okay, so to find the frequencies, what I need to do is to call the sampling freq is equals to the same way we did the FFT. We need to call the Scipy func library, and then sp.fft pack, and then in the FFT pack we have the freq, which is why it's not coming out, FFT pack dot f I think FFT freq. I don't know why the I'm pressing tab, but it's right there, FFT. Okay, and then the input is going to be the length of so our original signal t, which is going to take the length, and then another input will be the time step. Okay, so that is delta t. Remember, we defined the delta t, or sampling frequency, the sampling rate. So now we are going to, when we are going to get the sampling. Okay, so let's plot it out, plot our power density against the sampling frequency. So let's say plt dot plot, and then our x level is the sample frequency, and then we have the power density, spelling power density. Okay, let's plot it out. So okay, here we have it. Okay, so you can see the frequency and the power density. We can do one thing, let's trim it. So let's normalize it. So let's say max of the power dividing it by itself, so maximum of power density. Okay, so that this y axis is going to be normalized then. Okay, so power density. Okay, so you see the maximum value is 1 now, and now it looks much more better. Okay, and then what we can do just to maximize this figure, so plt dot axis, and then let's say we are starting from -1 in the x-axis, -1 to 1, and then the y-axis goes from y-axis, we are not doing anything, 0 to 1. Okay, so plt dot axis, and I think we need to just copy this thing, and just need to be here. Okay, so let's run this cell again. Okay, now we are zooming in a bit here. So you can see like the frequency component is at 0.5 and -0.5. Okay, so a couple of things I would like to mention. Here you can see like it's roughly about 0.5, which is what we expect right here in the frequency. But how about increase the noise a bit? Okay, So let's say our random noise, let's say it's 20. Okay, and let's see how the frequency component looks like now. Okay, let's run everything, all the lines, and this is kind of, you see this some broadening here, some more noise popping up. So it's getting worse, but still you can say like, okay, our FFT is able to get the frequency component of the maximum, where the maximum power is located. Okay, but I'm pretty sure like if we add more noise, more random noise on it, and this is random, right? So if you run it like 10 times, 15 times, then there will be occasions where it is missing the actual frequency. Okay, but this is a simple way to just to show like how can the FFT algo work. So you can just, you're welcome to explore more on it.